So this may be the shortest of all the videos on calculus, but this is the one that talks about higher derivatives. And the basic idea is that since the derivative of a function is itself a function, then we can differentiate again to find what's called the second derivative. And the second derivative is indicated in one of two ways. So again, we have our differential notation, and so to indicate that we're taking the second derivative, well, it's the derivative of the derivative. So df dx is our notation for the derivative, and d dx is our notation that says differentiate whatever follows. So second derivative is going to be indicated this way. Or I can combine these, and again, it's not a fraction, but it helps to explain the notation. There's d times d squared, and dx times dx, which you write as dx squared. And so this is our commonly accepted notation for the second derivative, but all it is it's the derivative of the derivative. Prime notation's a lot easier. Again, the derivative of the derivative, I can indicate derivative using the prime notation, and I'm differentiating the thing here, which is a derivative. And again, in our simplification of the notation, this is going to be f prime prime, usually read f double prime of x, as our second derivative. And I could stop here, and that's actually everything you need to know about the second derivative, provided that you understand what the first derivative is. So if you understand what the first derivative is, what it tells you, the second derivative is, do the same thing again and it'll tell you something else. That something else tends to get a little bit more complex, but finding the second derivative is not any more challenging than finding the first derivative. So if I have a function x cubed plus 3x plus 7, well, the second derivative is, keep in mind, this is just the derivative of whatever the first derivative is. So all I need to do is figure out what the first derivative is. So I want to differentiate my function x cubed plus 3x plus 7. So derivative of that, 3x squared plus 3, still need to differentiate that. So my second derivative is 6x. And we can find other derivatives. So here's v equals some complicated function, and I want to find, using differential notation, second derivative of v. And so again, that's the derivative of the derivative. So that's the derivative of v. And I know what v is, so I'll substitute that in. And a little bit of analysis goes a long way. The thing in here, substitute in a value for h squared plus 3h plus 7 over 2h minus 5. The last thing you do before you evaluate this expression is to divide. So I'm looking at the derivative of a quotient, so I need to apply the quotient rule. So applying the quotient rule, bottom times derivative top minus top times derivative bottom, all over the square of the bottom. That's my first derivative, but I need to differentiate again. And here's one of those few cases where it might actually be worth doing the algebraic simplification. So I'll expand the terms in the numerator and simplify and collect like terms, so I end up with something that's a little bit easier. Again, important note, all we've done here is algebra. We have not yet differentiated anything. This is just a purely algebraic simplification there of original fraction to slightly easier version of the same fraction. And again, we see that this function is a quotient. I take this, I divide it by this, and that's the last thing that I do. So when I differentiate, it's the first thing I'm going to worry about. So applying the quotient rule, that's bottom times derivative top minus top times derivative of the bottom. Don't forget the chain rule, all over bottom squared. And that's the second derivative. Well, a good rule in math is that if you can do something once, you can do it as many times as you want to. So I can actually go beyond the second derivatives and find higher derivatives. For example, let's take a look at something like this. And here the hardest thing to read is how many derivatives that is. So if you look closely, that's 1, 2, 3 prime. So this is the third derivative for this function, square root 8x plus 7. So there's my function, square root 8x plus 7. Conveniently, I might consider that to be 8x plus 7 raised to power 1/2, so that when I differentiate it, that's going to become chain rule 1/2 whatever power subtract 1 times derivative of the inside. Maybe do a little bit of algebraic simplification. Well, there's my first derivative. Well, my second derivative is just going to be the derivative of that, so I'm going to differentiate again. Exponent comes out front, everything else stays in place, power drops by 1, don't forget the chain rule, and there's my second derivative after simplification. Third derivative, I'm going to differentiate one more time. So again, exponent comes out front, everything else stays in place, power drops by 1, don't forget the chain rule, and do whatever simplification you feel up to doing at this point. And there's our third derivative.